organizers are not yet here, but definitely soon. And right now I am Yash, and I am delighted to introduce Nico to the first speaker today.
All right, good morning, everybody. Thanks for coming so early. So it's a great honor to be here. So I'm really happy to take this industry perspective and tell you a little about how some of the matching markets or matching in general that we've been discussing in the last few days apply to things we do at Facebook and things that other companies do. So what I'm gonna do today, instead of like choosing one paper and going deep in that paper, is to give you an overview of different things we do at Facebook to try to run products and inform these products from decisions that have to do with matching markets and how we can scale these so we can do this, with big markets, with many items on both sides of the market, and also how to run this accurately. And what I'm going to be presenting today are basically material was taken from different papers, different projects, and slides were also taken from different people, thanks to many of them. Many of them are co-authors of mine or people who work with me in different projects. All right, so matching markets. So a matching market basically appears in many places at Facebook. Things even like feed. If you look at Facebook feed or Instagram feed, you can think of that as a matching market in the sense, or a matching problem, in the sense that you have to map posts to users in some way and then show those posts to those users. So what you're doing is you're trying to match two sides of the market. And when you look at these problems that appear, and I'm going to give you many examples throughout the talk, basically there are different things you have to consider. The first one I mentioned is scale. So we need to solve these problems, and these problems are super large. We have millions or billions of items on one of the sides of the market, and you need to solve them usually very fast. If you have to render a feed, you have a few milliseconds to do that operation before you have to transmit the web page to the user who's going to be looking at that. As you start modeling, the other thing is also you need to be accurate. So many of these problems will rely on the data that describe the problem. The data may be the nodes on the two sides of the market, the edges that connect the nodes, or even the weights that will be on the edges. And usually people use machine learning to learn some of those weights, and the question is how to do this properly so the outcome of these, of the solutions of these problems make some sense to then inform what you're going to be doing. In that context, you have to deal with many side constraints. Like one of them would be that you want the solution to be fair or equitable in some respect. I'll give you a few examples later. Or other side constraints. For example, you may not want to be, it's like all posts like one after the other to be of the same type, because you may want some diversity in what you get. Also in real life, you have to deal with the problem being stochastic or online. You don't have all the information beforehand, so you have to forecast what's going to happen. And depending on the nature of the problem, you may take that as an online problem or a stochastic problem of different kinds. And then in the context of markets, there are these two-sided aspects that maybe the two sides need to grow at different space. You want to balance the sides, and there are things that you want to do there. So these type of matching markets have been looked at from different perspectives. So one of them would be to look at the flow problem, and that's one I've used a lot in the past for solving this type of thing. So you can associate a super source and a super sink and solve the flow problem there. But actually matching markets can be and have been looked from many different perspectives. So flow, network graphs, you can look at this as a sorting and ranking type of algorithm. Some people in machine learning have been looking at this type of thing, in which you not only look at the assignment, but when you look at a fit problem like the one I mentioned earlier, you want to see in what order you want to display all these items. You can also look at these as recommender systems, in which maybe you know that a given user look at posts of a given kind already, and you want to recommend the next type of post that the user may like. So in practice, like in a big company like Facebook, there are many groups that specialize in different things. And when you take any of these problems and you talk to the engineers that are engineers and product managers designing a product, you need to have all these views. And depending at the end of the day, what groups end up collaborating in a project, like you'll have all the inputs from people that are going to be looking at the problem from any of those perspectives or all of those perspectives at the same time. And you have to make some sense out of that to try to give a recommendation of what to implement to make some sense out of the problem. And this goes at different scales or different scopes. So at some point, for example, you want to design the product and you want to make decisions about how the product is going to behave under different conditions. So that's one aspect. The other aspect is that after the product is designed, you may use some of these ideas to then guide the operations of the product. So for example, solve a problem and based on the solution of the problem, maybe rank the feed or recommend something. So all these perspectives are present in everyday life in a company like Facebook. So the goal basically is what I was saying. So we have a very complex system that is typically dynamic where users may come in, go out, churn, and things are happening all the time. What you like to do is you like to capture the essence of those in a very simple model, and I highlight that can be solved. If you cannot solve it, then it's not very useful to you. So you need to be able to solve it, and then that solution you're going to be using to either like take the strategic view and help you design the product, or take the operations view and help you guide the operations of the product. And as I said earlier, the blockers are you need to be able to solve it first, and then the solution needs to make some sense. So you need to be able to calibrate it so you can forecast really what would happen if you were to actually implement what the model is capturing. So how to do all that is really some of the challenges that we run into every day. So for this talk, and initially I want to take the perspective of matchings from a marketplace design, so like a market mechanism. But I want to do that in a way that you look at the market from behind. So for example, if you look at the ad auction in which every time a user comes up, we run the auction to decide how much to charge and what ad to show to whom. Instead of looking at that auction per auction, we want to take it at a distance and then look at this market as a market, so like as a competitive equilibrium market. And then from there, try to understand what are the prices and what gets assigned to who. So that's the perspective I'm going to take for this talk for now. So if you look at market equilibria, basically what you get as inputs is an instance of a matching market or of a matching. You get buyers and you get items. Typically you have budget for the buyers and supplies, finite supplies for the items. You have preferences for the buyers, so what items they prefer. For the items, they have prices, and what you want is the market to clear. So basically what you want is you want to set prices such that supply equal demand, and you want to set allocations so the buyers are happy with the items they got. And all this has been studied like very much, and there are algorithms and there are many properties that are known for this. So one view we can take is for these type of matching markets, we can solve using this concept of market equilibria, and then we get automatically many of the properties that we know that these objects have. So the views, I'm going to take this, the CEEI type of market equilibria. So if we want to solve one of these matching markets, we can ask everybody what their preferences are. We can give people some fake money or real money, depending on the situation. Depending on the situation, also, you can come up with a goal and a utility function for the goods. For the buyers in this case. So it can be quasi-linear, would be the utility of the goods plus the money they are left with. If money has no value, then it's just the utility you get from the goods. Then you solve the problem, and you take that output to then guide either your product or your algorithm to be able to do what you need to do. And this has been used in many cases. I have some examples here. For example, in business schools, so for MBA programs, students are given this fake money, and they can bid for courses, and we can use these type of arguments to assign students to courses. So as I was saying earlier, so the hope is that we can use these type of objects to then guide the operations and understand what we want to do in these type of settings. One of the big things that happen in practice is that when you have a complex product, you may have the product be interacting with many other products in the company. And one of the issues that arise is that you have trade-off between different metrics that different parts of the company may be pushing for. And what's not clear in practice is what these trade-offs are and it's hard to quantify in practice. So one of the goals would be to, through these models, to be able to understand these trade-offs and see, like, under different operating parameters or different proposed mechanisms, like what happens between the metrics. So if you can solve these models for, for different realizations or different variations of what's going to happen, then you can quantify precisely how these metrics are going to look like under different operating points. And that's one of the goals of being able to model things in practice. You can also answer what-if questions, counterfactual questions. What if we subsidize one side of the market? What would happen? Or what if we change the way that we connect, like, the left side to the right side, so we have a more dense graph? What would happen with it? So through these type of approaches, we can answer these questions. We can also answer another important question, which is one that happens in practice, that engineers go and implement an approach. Usually they implement a greedy approach, which is the easiest to code and then to roll out. So now I have a greedy approach, and people ask you, well, how good are we? So if you have a model of this kind, then you can also solve for optimality and then look at the benchmark of how well you're doing compared to the best you could do, at least if you believe that the model will give you something concrete. So in some cases, maybe you're not able to solve the model in the time that you have to really make the assignments, but you can do this offline. At least you can do it to compare and see how far you are from optimality in those cases. So for today, what I decided to focus on are on two sides. One is about scale, as I said, so how one can solve problems that are large in the setting of competitive equilibria. And the second part is about Bayesian optimization and how to learn a model so we can be accurate. So here are, like, some papers that refer to that I'll point some of the main results there in the talk, but those are references so you can look at them later on. So let me start with an example. So if you look at the ads market at Facebook, so the way this works is that we have advertisers here that decide who to target for ads. So for example, this jewelry firm will decide to target all females, and this e-retailer will target everybody, and this fashion firm will target young adults. So now the way this works is when a user shows up, for example, this woman who's 24 years old shows up, we look at all the ads that target her, and then we run the auction. So all these advertisers will submit to the system a budget and a bid, and then using those bids, we run the auction, and whoever wins gets to show the ad to that particular user. Now, as I said earlier, like, if you model this, you have to model, like, auction per auction, what's going to happen, and that may be complicated. So one way to look at that, and this is what we've done, like, in these papers, like first and second price pacing papers that we work on for the last couple of years. What we do is we look at this from the distance and try to solve this system as a competitive equilibrium. So if you look at this from a competitive equilibrium perspective, then what you have is you get prices for all the users, and then the assignment is going to happen automatically from that competitive equilibrium. And then you can understand how the system is working, and you can use that to then make some of your decisions. And one of the ideas that's going to come recurrently in the talk is that if you have such a system, you can use it to predict, but sometimes the predictions may or may not be perfect. So what you can do then is you can complement the predictions with some small experiments to try to calibrate those predictions. And then using the combination of the modeling and the outcome or the output coming from these assignments and a limited number of experiments, then you can learn what to do without a lot of online work that is very expensive and time-consuming. Okay, so one of the goals of the talk today is also to present you with some of the different matching products that we have at Facebook, because some of them are slightly different. There are different things that we can do with them to try to improve their design and try to improve their products. Some of them I'm going to be speaking about now are in the area of social good. So one that we had a talk yesterday, maybe some of you were here yesterday, is around blood donations. So what this product does is to try to match people that are willing to donate blood to blood banks, hospitals, or other people that need blood. And what we do there is to people who register as donors, we provide recommendations about places they can go to donate blood. So again, this is directly a matching problem. There are some particularities that people cannot donate blood too often, so we need to deal with that. But other than that, it's just having the supply, demand, the weights between the two sides, estimating those weights, and then solving this type of matching or ranking or recommendation systems. You can view this problem from all the perspectives I mentioned at the beginning. So that's one example. Another one is on fundraisers. So when you do charitable donations, there is a feature by which you can match what somebody donates to an NGO. So somebody can say, hey, I have this money, so for whoever donates to an NGO that I'm interested in, I'm going to match the funds. So one of the questions here is what are good ways to incentivize more people to donate? So again, in this case, what you're matching is your dollars that you're putting there as contributions to donations that a person makes to an NGO. So what's the best way to match those dollars to other people to try to incentivize more people to donate? Oops. Another product that exists at Facebook is this one in which we recommend mentors to mentees. So this is part of groups. So at Facebook, there are groups where people can enroll to talk about a given topic usually. So in some of these groups, you can designate as be part of this product, the mentorship product. And what this does is that people can enroll as a mentor or as a mentee. And what the product does is to then match mentors to mentees so they can have a conversation and learn more about something. So I've used this as an example. I have a daughter who's gonna be going to college next year. I have no idea about how to apply to colleges in the US because I haven't been to college in the US. So I enrolled in one of them, and they gave me some feedback about like what are things I can do to try to cater to colleges that are aligned to her interests. So this proved useful to me. And from a product perspective, the question is what's the best way to match mentors to mentees? And again, it's like a standard matching problem. This is a new product. This is not part of Social Good, but it's a product that launched a couple of weeks ago, Facebook Dating. So in this product now, people can create a new profile, which is not mapped to the actual Facebook profile of people. This is Facebook and Instagram. And what the product does is to then match people that may be your partner, people you may date. And yeah, so this is a new product. Launched in the US recently. It's been active in 20 other countries for some time, I think the last year or so. And yeah, we'll see. So I'm looking forward to see how this goes in the US. So one of the features of this product is this secret crush, in which you can list some people that are your people that you secretly love. And then if everyone does that, if there is a match, then we may mention that, hey, so this pair is a pair of secret lovers, so you may want to talk to that person. So I think a nice question for our background is how to make that feature incentive compatible so it cannot be gamed. So I think that's an interesting question. So I think the way that has been implemented, there is some friction and people cannot change that too much, so you cannot explore too much. But I think that's an interesting question about how to come up with good solutions for that issue. One thing I want to focus on in particular is on this job application. So another thing that happened at Facebook is that people have been using the platform to look for jobs and to offer jobs. This happened organically and for a long time. So there were groups that existed about finding jobs in given geographical areas or for given topics or type of jobs. So at some point, Facebook realized that and decided to create a product around this. So instead of writing text in a group about, hey, so I'm looking for a job of these characteristics. So what the product does is you can input the type of job that you're offering, so to try to solicit applications. And then for the seeker side, you can rank and list some of the jobs that are available in your area for some characteristics. So you can look for full-time jobs, part-time jobs in a given area, in a given type of category, and then you'll see a list of jobs that are offered. So you can apply to it, and then you're matched to the company, and maybe you're going to be interviewed if you do. One thing we know, so that's again is a matching problem, right? So we have many job seekers, we have many jobs, we need to match one to the other and recommend to job seekers what jobs they may be interested at so they can apply. One thing we noticed that when we started running this product is that there were some congestion effects. So basically, that some jobs got many applications and some other jobs got fewer applications. So the question here is how to balance the market. And that goes into what I described at the beginning, which is we want the matching to be somewhat fair. We want people to not regret the type of recommendations we're giving them, so everybody has access to all the jobs. Here, in theory, you have access to all the jobs because you can scroll forever and see all of them, but what we put on top is important. So how we can balance that market so most people have access to most jobs that are relevant to them. So that's why we want a fair allocation when we solve these type of matching markets. So as we think about this, so if you look at this ranking and you solve greedily for some type of value model and then you sort from top to the bottom, you can do some centralized optimal matching to do that. And that, you may need to ad hoc try to add all these fairness constraints to make sense of being able to balance the market. Or you can take it a step further and then look at this from some of these marketplace perspectives to try to have this automatically. Yes?
Learning involved, trying to learn someone's preference, what kind of jobs they want to do.
Yeah, totally. I mean, that's the main issue. So the question is there learning involved? So yes, indeed. So we don't know the intrinsic quality of every job that gets posted. So we can try to learn through how people interact with these jobs. So if many people click on the job, if many people apply for the job, which are things we know because people click on these buttons. But you also have the risk of, getting the rich get richer effect, right? So if by some random coincidence too many people apply to this job, then we think it's really good, and this is going to be more likely to be shown in the job feed of more people. So I guess what we like is we'd like to have enough exploration so all jobs are given some chance so people can learn the true quality, and then from there we can continue ranking. So how to do this properly is the key to this question. Okay, so all these examples, what do they have in common? They're all matching markets. So we have, in this case, jobs and seekers, we have the evaluations, and then the harder thing here is to learn the weight that will go into these links, which is the learning that we were just talking about. But if you can do that, so the question is how to learn properly, how to expose more jobs to more seekers so we can learn the true qualities in a good way, and what are the right machine learning models that we can do there. And after we've done that, what's the right way to match one side to the other and rank? This is probably well known to most people. So one of the advantages of this competitive equilibria type of model is that you can solve this as a convex optimization problem. So you can write like a centrally an optimization problem, solve for it. This may be easier or harder as a convex optimization problem. But if you can solve this one, then you have an output for this. So you can think of these market equilibria algorithms as any other centralized matching problem that you can solve. Instead of using an LP or an integer program or a linear program, use this convex program to solve. But one of the issues is that both a linear program, integer program, or convex program, they don't scale that much. So when you have millions or billions of items in a side, maybe you can even fit in memory all these variables, so to be able to do some iterative algorithm to be able to solve that. So one of the questions we had is how we can do this in practice. Before we go to solution, and this I mentioned earlier, this competitive equilibrium gives you many nice properties around regret, envy, being Pareto optimal, solving Nash welfare. And so there is a new paper that some of my co-authors have, is that you can even add constraints of the kind that you can assign at most one of the other side to this without breaking some of the structure about the convex problem I told you earlier. Yes?
What about revenue?
What about revenue? Yeah, so revenue is one of the metrics. When I told you earlier about the trade-offs. One is welfare, the other will be revenue, depending on the type of product. So if we look at jobs, there is no revenue, so we're trying to make the best assignment. This is not monetized. If you look at ads, there is revenue, and then there are trade-offs between revenue and welfare. And through this, you may want to look at those trade-offs and select the operating point that makes sense to you.
But in competitive equilibrium, do you tax this transaction?
Well, it depends on the model you select. If you're using real money or on fake money, depending on that, you can be paid, and if you're paid, you can look at your revenue. If it's fake money, you're looking to maximize welfare with the sum of the utilities of all the users. So depending on which of these models you're looking at, you may incorporate that or not, depending on what you need. So let me now mention a little about how to solve this in practice when the market is large. So we have the product, which is this market that we've been talking about, that you can abstract as a matching market, right? So this is the real product, this is the abstraction. This is my matching market, the two sides with the values that we mentioned earlier. But that's the one I mentioned maybe is too large for us to solve. So what we came up with is this idea of taking a compact representation of the market. And I have a slide about it later. So the whole idea is that to come from the abstracted market to the compact market, what you do is you may take a low rank approximation of the evaluation matrix, or you can do clustering between like the two sides of the market and then take a smaller market on the two sides and then compute the edges and the weights of the edges in a way that is compatible with what you had initially. Now you have a compact market. This is small enough so you can go ahead and solve it. So when you solve the competitive equilibrium, now you have an assignment and you have prices for the goods in the item. But this is not good because this is really far away from the product, the original product. So what you do is you can lift it to the original abstraction here. And there are different ways you can do that. But if every one of these nodes was representing a group of the nodes when you did clustering initially, you can project up and then you can assign, you can try to take this representative assignment and then assign it to the abstraction you had initially. And same with the prices. So you have prices for the goods, you need to come up with prices for this bigger market that represents reality. And now you have a solution to your abstract model, but this is like real size of millions or billions of items. And now you can use this to try to get some insights or make some decisions for a product. So this is what I mentioned earlier. So the two ideas that you can apply concurrently are clustering and using low rank approximations. So if you cluster, you can cluster both the goods and the buyers. Each of them will have some features that will describe the goods and the buyers. When you do like k-means or any other clustering algorithm, you can get the representative for the features that describe the buyer or the good. And then this is what gives you the smaller compact market. You can find the weights by taking, for example, the inner product between the two sides of the market. That will give you the weights, and that will give you a smaller matrix that you can use to solve this problem. Some of the properties you can get from there is that now, if you project up to the original space of the big market, now you have a new matrix. This new matrix will represent the clustering or may represent the low rank approximation of the original matrix. So one thing you can prove is that like some of the metrics that you wanted, like envy, regret, welfare, etc., are bounded by the distance between the original matrix and the compact matrix. And you can prove this. So in a way, what I'm saying is that as you compact, you're not losing too much. So it won't be exactly envy-free, but it'll be approximately envy-free, so that's kind of fine. The second property is that as you project up, you're not losing too much either. So you can go back to the original solution, to the equilibrium for the original abstraction, and that's not too bad compared to what you would have done if you had solved the original market. Yes?
Just for clarification.
Yeah.
So the W's entries are utilities, right?
In this case, is the utility of any good for any buyer. Yes, exactly.
And prices are on one side and budgets on the other side.
Exactly, yes. But the prices are the outcome of this, not the input, right? But yeah. Yes, question.
W is also a probabilistic quantity, right? So because it can be a preference of a job to a seeker. So in that world, when you cluster, the probabilistic view is gone, right?
I think you can interpret the same way as you interpret the original one. So the usual interpretation of these matrices is that that's the utility you'll get if I were to assign you to that job, right? In that sense, it's deterministic, it's not probabilistic, right? So this is the basic definition of competitive equilibrium, it's deterministic. So I take the abstraction now. This is not the exact utility. It's going to be a representation of the utility I would get if you take the representative of that cluster of jobs, because you don't have the real one in that one. Yes?
Why
Could we use a clustering algorithm instead of projecting it to characteristic space?
I think that's another idea of what you can do. So we tried this one. I'm not saying that other ideas cannot be tried. Part of the reason of me presenting this is to like elicit others to be looking at these things. So yeah, there are many other ways in which one can project into a more compact representation. So this one, yeah, seemed to work, and we're happy with it. But I'm not saying that others don't work.
So one question is, you have to know the utility somehow or guess them.
Yes, indeed. The utility will be the edges, the weights of the edges in the matching problem, and you have to apply some machine learning or some other way to learn those weights. Indeed.
It requires more input than auctions, because auctions you need not know the utility.
Well, in the auctions also, if you participate in the auction, I have to bid for different people how much I'm willing to pay. So, in terms of information requirement, it's not different from what you would get in an auction. Yeah, exactly, the business utility. So if you try these ideas in practice, so we did a simulation study in which we took a matrix and we tried this for different ways, different abstraction levels. So we condensed the market in the two ways I mentioned by taking clusterings and by taking low ranks. And the question is, in practice, how far are we depending how much we compact the market or how much abstraction we take. This is a busy slide. There are many graphs, but say take any of them, for example, MB. What this says is, depending what percentage you take the abstraction, so one would be 100%, you take everything to 0, it means that you compact it a lot, meaning that for every cluster is very large, so you take only a few representatives, and the colors represent to what rank in the matrix you are taking. So this is saying, like, as you compact, how much you lose in terms of the maximum MB you may have. And so as you see, the curves don't decrease too much. It means that you're not losing too much by taking these compact representations. So that's kind of what I want to transmit with this. There is an approach that seems to work in practice, that we can compute equilibria that makes sense, and from there inform some of the operations I described earlier. I have time until 15, right?
So what's the structure of a market where this approach will do like really bad?
Say again? Sorry.
Structure of a market, right, where this approach will do really bad.
What's the structure of the market in which this approach will do really bad? I didn't try to take a worst case approach to this. So we have the theoretical bounds that tell us how bad it can do in a worst case. When we try this with actual instances coming from real markets or real matching problems, it seemed to be doing things related to this. But I haven't tried to compute the worst case that will match the worst case bounds that we have here. Okay, so given I have another 10 minutes, I want to focus the second part of the talk in also telling you about like some of the weights that happen in practice. How do we compute them? How do we make sure that these models make some sense in practice so we can inform the operation in the right way? So in this second part, I'll talk a little about Bayesian optimization and some of the mix between these centralized solutions we have been talking about so far with what happens in practice. So other keywords or other interesting things around this is how to deal with exploration and exploitation and how to work with trade-offs between matrices. And the type of things I will be talking about have been open source in these two packages that are available online. So Axe and Blowtorch are there on the web. So if any of these looks interesting to you, you can go to those web pages. There are many tutorials. There are many ways in which you can learn more about this and try this out if that's useful to you. Okay, so going back to these weights, how do we learn the weights? How do we make sure the model makes sense in practice? So it's a big world. There are many people living in different places, different conditions. It's really hard to learn things properly when you're exposed your things to many different people in the world. So what people have been doing traditionally has been to run experiments. So you have a theory that something may work. Maybe there are a few parameters. You don't know how much they are. What you can do is you can run a few experiments. You try your parameter at certain values. Then you measure the outcome of this. Maybe you measure the engagement. You may measure the welfare or the revenue or how many videos are watched or how many posts are read, whatever it is that you care about, you measure that. Then you try again with new combination of parameters, you measure all those metrics again, and you keep doing that until you are happy with something that seems to work. Like a concrete example would be feed. So the way feed works is that if a user comes into the platform, there are a number of items that can be shown to that person. Typically, somebody in product decided that a way to rank is through some value model that has many terms. The terms may have to do with how likely you are to click on that item, how many friends the person you're talking, the person who wrote the post has, what's the strength between you and that person in terms of the tie, what's the probability that that post is spam, etc. Right? So there may be many other terms here. Like how to weight between those terms. So typically, engineer doesn't know, so what they do is they add a constant in front of each. Maybe you add an exponent, or maybe divide by something. But you don't know we don't know how much these numbers are, so we need to learn those numbers to make sense of that value. If we have these values, then rendering a feed is just for every possible post, we compute that, we sort from top to bottom, and that's your feed. But the question is how to learn these numbers so the feed makes sense in practice. So this is hard. People, as I said, have been running experiments for this. Some people decide to write a simulator so they can interact with this faster. So they wrote this simulator. The problem is the simulator, when it was contrasted to some experimentation, it was super biased. So then if it's biased, it's not easy to make decisions on something that is biased because then the decisions are going to be wrong. So the question is what to do. And this is kind of the end of the story. This is some text taken from a post by an Instagram ranking engineer that says that we've seen significant improvements over the years by tuning this value model. We typically use Gaussian processes and Bayesian optimization to do that. And here you can plot the surface of, for example, for 2 of the parameters, there are more, but this is only 2. This is like some metric how the shape looks like, and you like to optimize that to take the maximum point there. So the question is how to learn that surface efficiently. Yes?
How does the engineer know that they're doing better?
That they are doing better than what?
How do you even measure whether you're doing better?
Oh, you can run an experiment. So say you change this, you multiply this number by 2, right? So you run a new experiment. So you select 1% of the users, you expose them to a new feed, you measure how well the platform does in that experiment, and then you compute the treatment effects for that feed, so you know it's better than production.
Just thinking of clickbait, where like clickbait is like just this example of something that looked really good in some of the metrics, but Facebook tried to get rid of it because they kind of have other things.
Cool.
And when do you trust the metrics?
That's a great point, but then, so that point is about whether you're using the right metric, not whether you're optimizing that metric. So yeah, totally. So that's a discussion that happens all the time. So for example, you may want to increase the number of users you have in the platform, but if the users include the fake users, then you're bringing more fake users to the platform, which is something you don't like. So the right metric will be the number of real users, not the number of users total. So coming up with the right metric is a problem in itself, and it's very important and interesting. So, okay. Yeah, thank you. So what we need to do is we need to find these edge weights properly, and that's not easy. To do that, for many different problems, we need to tune parameters, so maybe through the value model, maybe through another machine learning model, maybe you are running different regressions, logistic regressions, or different kind of regressions to know what edges are there or not. Maybe you are using deep learning. So whatever it is that we are doing, we may need some parameters. So the question is, what do we do? So one thing that is generally the case is that the outcomes are often smooth in these parameters. So if you change like one of these parameters a little, things don't change that much. So if you can take this smooth view, then what you can do is you can try to keep learning by, sampling from the parameter space, learning through an experiment what's going to happen, and then sample again. So that's the whole idea, is to have these iterations. So we take a parameter, we take a vector of parameters, we evaluate with experiments, we fit a model, and that will give us new candidates to try new parameters. So traditionally, what people have done is they look at this grid search. So you try like all parameter combinations in some space, but the problem is that that doesn't scale if you have too many parameters. We cannot take all grid points in a big space, because that means that you have to run too many experiments and you don't have enough time or users to be able to do that. So that idea doesn't really work in practice. So the idea that does work in practice is Bayesian optimization, which has been used successfully by many people in the company, in many other companies. This is very common these days. So what you do is then you have, up to some point, you've run a few experiments. So you have some confidence interval around the metrics for different parameter points that you already tried. Oh, this cannot be seen, but here you have a confidence band that is hard to see in the slides. And the confidence band, like maybe very narrow in the cases where you run the experiment, and really wide, like here, in the places where you haven't run any experiment, so you don't know really. So what you're trying to manage some exploration versus exploitation. So what can you do? So at this stage, you can say, look, this looks very close to optimal, and I have very narrow confidence interval here. So maybe I want to exploit that and keep doing this type of parameter. Or you can say, look, here I have an estimate that is high, and the confidence interval is really wide, so maybe it's even higher than what I have there. So maybe I want to keep running experiments in this region. So what you can do then is you can compute the expected improvement if you were to run the next experiment in a different parameter. So this is what I'm plotting here. So what this gives you is then what is the next candidate that you should run. So now the next candidate is this one. It means that what I should do next to solve this exploration trade-off is to run a new experiment at this point. And then you keep doing that. So this has been used a lot. So as I said, it's hard to run so many experiments. So the way this works in practice, if you want to make this more efficient, is to complement this experimentation platform with some other way to run, either simulate or solve models in practice that doesn't involve experimentation. So what we do is we do the two things together. We draw from the experiments and from the simulation, and we try to put all that data together, fit a model, and then continue exploring and generating new candidates. Yes?
Since you are using PCA or low rank at some point, if you assume the structure is low rank, that might help estimate. For instance, recommender systems.
Yeah.
Do you use something like that?
Oh, yeah, exactly, yeah. So from if you know something is low rank, you can use matrix completion, other things like that, to try to guess some of the things. So the more you know, the more structure you can impose to these models, and the faster you can learn. So the whole point then is to put everything together. So you have the simulations, you have some of the online experimentation. Simulation is cheaper, so you can run many of those. You run a few of the experiments that are more expensive. You create a model together with all that, and that will give you a new candidate that you keep iterating. And those are just a few graphs in which you can see how the simulators are biased. So if everything was perfect, you would get points on this line, but you don't. But if you complement this with some of this online experimentation, what you get is that things get unbiased, and you get the right operating point for different parameters. And now that you know this, now because your process you can simulate offline in a right way, now you can optimize over that and take the maximum, which is what you wanted. So that's an example of when you optimize feed using Bayesian optimization. In each of these batches, you add more of the experiments and more of the simulations, and you can see how the metrics is going to come up close to the optimum. Okay, so to conclude, so this is type of the how you iterate with this. BOTORCH is this package I mentioned earlier, which is the Bayesian optimization package that will allow you to optimize under uncertainty, whether you know the right structure of the function. So you make some assumptions, you need to learn the shape of the functions, and through Bayesian optimization, you can keep generating new parameter configurations. Through Axe, which is the other package we open source, is the one that will run the whole process. You will do the bookkeeping of taking all these parameter combinations, generating more simulations, and doing the whole thing. So between the two, basically, you can try to optimize your metrics and achieve these goals that we talked about. All right, so to recap, I try to give you like an overview of different things we do to try to improve some of the products using techniques coming from matching markets, optimization, and the type of work that collectively in this room we deal with. And the whole idea is that through being able to improve the scale and the accuracy of these models, we can inform both the strategy of the products and the operations of products in the right way to go back to the engineers, product managers, technical project managers, etc., and try to help them guide the decisions that they do in the projects. Thank you very much.
Maybe we can have one quick question while Peter sets up. Yes.
Are these slides available somewhere? Are there papers?
Yeah, there are papers. Yeah, the papers are there. I can try to post them. I'll talk to the organizers to see what's the best way. Otherwise, feel free to ping me. I'll give you my email. Yeah.
Was your talk recorded?
It was, yes. The talk was recorded also. Yeah, yeah. Do you need my charger or can I take it out? If you're recording, probably need the mic.